Okay then, so for the next chapter we're going to talk about chapter 6, Finite State Machine. So I think you've probably heard of this before in your previous digital design course. So finite state machine is a critical component, okay, in a sequential machine design. In practical design there is almost always FSM, a state machine. It is important because basically with the state machine we can control the sequence of operations. Okay, for example, at this moment of time you want to do X operation, and after we finish X you want to do Y and then Z and so on, so that we can control by using the state machine. So basically in this chapter we are going to go through in detail on how to design state machine models using Verilog and how to analyze the models. So basically here we are going to go through in detail for 6.1 ASM chart and state diagram, and then going to look at the modeling of FSM in Verilog, the Moore and the Mealy model. I think you have heard of the Moore and the Mealy model. And then we're going to go through some basic examples. Okay, so 6.4 and 6.5 are more advanced topics that we're not going to cover these two. Okay, so these are advanced topics. If you are interested, you can read through by yourself, but we also have our postgraduate master course where we cover the more advanced constructs in Verilog. Okay, so let's go straight into the first part here. So you can read through this yourself, but basically for FSM we have the Moore and the Mealy model. Okay, so just a recap, I think probably you've heard before the Moore and the Mealy model. So what's the difference between a Moore state machine and a Mealy state machine? So let's look at the Moore model. So in the Moore model, basically you can say the output depends only on the present state, or PS. Okay, so as you can see here, to generate the output we only need the present state variables, or the PS. Okay, on the other hand, for the Mealy model, okay, so the output depends on present state and the inputs. Okay, so as you can see here, to generate the output we require the inputs and also the PS. So that's basically the main difference, or the only difference basically, where if you want to generate an output that is based on the current state and also the input, then it's called a Mealy model. Okay, however, if you want to generate an output that depends only on the present state, doesn't depend on whatever happened to the inputs, then it's a Moore model. So the easiest way to remember this for me, you can say that more is less. So more is less. Okay, so meaning that a Moore model will have less signals, means the output doesn't contain the input. Okay, so this is basically the functional block diagram, you can say. These two are very important. Okay, very critical, very important to understand how this thing works and what are the components. So you can see here, basically the components we have the net state logic, state register, and output logic. Okay, the net state logic takes in the input and also the present state. The state register takes in the net state variables, and the output logic takes the present state variables. And then of course we have the clock reset that goes to the state register. Okay, so similarly here with the Mealy model, the net state logic will take the present state, you will take the input, and then the state register will take the net state variables, output logic takes the present state and the inputs. Okay, so you have to remember that there are three main components in the state machine functional block diagram, which are the net state logic, the state register, and the output logic. Okay, so let's look at one simple example. Before that, we're going to look at how we model the state machine. So here is the functional block diagram. Okay, the components inside state machine model. But to model the state transition and what is going on at every state, right? For example, at this state, I'm going to set a certain output, okay, or I'm going to check a certain input. So this is also very important. Okay, this one is not really important. We're not going to really look at the state block instead, the state diagram, but it's interesting to know. But this one is the important one that we need to understand, where in our ASM chart, which stands for Algorithmic State Machine, okay, Algorithmic State Machine, ASM, okay. So in the algorithmic state machine, we have, first of all, the state name there. Okay, the name of the state is S0. The state entry, okay, coming from the previous state, and then we have the output Z1. Okay, this is a more output, which means it does not depend on the input A. So here is our input. Okay, so when we are in state S0, we're going to output Z1, regardless of what happened to A. Now we also have a mealy output, Z2, which now depends on A and also state 0. So now you see the mealy output depends on the current state and also the input. Okay, and we see the box is a rounded box, here is a square box. Okay, so here is also we see what happened in the state transition based on the input. So if the input is 0, we go to this state. If the input 1, we're gonna do the mealy output and then goes to a different state. Okay, so it's a very important diagram there, okay, that we need to understand. And now let's look at a simple example of a more finite state machine. Okay, so here is our basically here is our so here is our state machine, a simple state machine. Okay, so here let's analyze this a little bit, a basic analysis on the state machine. Okay, so first you want to see how many states do we have? How many states do we have? Okay, so this is first we need to know, given this ASM chart. Okay, given the ASM chart of FSM1, okay, how many states do we have? So how do we know? So these are our states. Okay, 1, 2, 3, and 4. So here you can say 4 states: S0, S1, S2, and S3. Okay, how many inputs and how many outputs do we have? Okay, so inputs, I remember in our diamond. So inputs, you can say here A, and A. Okay, so one input A. Okay, what about our output? So output is inside the box. Okay, so our output is Z. So here we can say and here we can say Z equals to 1. Here is actually Z equals to 0 because there's nothing inside, and here Z equals to 1. So you can say 1 output Z. Okay, so now we know that we have 4 states, okay, based on the ASM chart. Okay, S0, S1, S2, S3. We have one input A, and then we have one output Z. Now can we get the functional block diagram? How does it look like? The functional block diagram from the chart. So it's quite simple. So remember, we're going to have 3 main components. Okay, so we have the next state logic, we have the state register, we also have the output logic. Okay, now what is our input? So our input is A, so A goes in. We only have one input. We have one output Z, so Z goes out to the output. Now how do you represent the states? Before that, we set our this is a DQ, so clock goes there, and then we have the reset goes there. Okay, so we have a standard notation here. It goes like this. Okay, so how many bits is the input and output to our state register? Okay, so here basically here you can say this is a present state, and here is our next state. and there are 4 possible states. Okay, so how many bits are required to encode 4 states? So here we can say, so this is 0, 0, 0, 1, 1, 0, 1, 1. Therefore here is actually 2 bits. Okay, so here is 2 bits. Okay, so 2 bits to represent our state. Okay, where if the bit is 0, 0, we say it's a state 0, 0, state 0. If the bit is 0, 1, we say it's a state 1. If the bit is 0, 1, 0, state 2, and so on. Okay, so 2 bit, and everywhere else is here is a 1 bit. Clock can reset. So that's it. That's the functional block diagram of the ASM chart. And once we have the functional block diagram, we want to write the Verilog code. Okay, so let's have a look at the Verilog code here that we do. So you can have a look at the state diagram there. You can read it through. Okay. Okay, so let's look at the code. Right here. Okay. So basically what happened here is we can derive the code, okay, from the functional block diagram. Okay, so let's do this quickly. Okay, so let's call it module FSM1. Okay, the input is a clock reset or 1 bit. Okay, we have the output reg, let's say it's a reg z. Okay, so clock reset. Okay, so here they call it the CLK and then reset. Okay, so 3 inputs and 1 output Z. Now the next line is we want to define our states. Remember we have 4 states, so that here is a new definition we call parameter 2 bits. S0 equals to 0, S1 equals to 1, S2 equals to 2, S3 equals to 3. Okay, so that's our parameter. And then we also have to define our PS and NS, they call it Y. So these are also 2 bits, so we call it small y and big Y. Okay, so these are basically the internals here. Okay, the internal small y and big Y. Okay, and then we have the parameter there. Okay, so basically what happened is we are going to define each one. So let's do the state reg first. The state register, which is this block. Okay, so what is the input and output to the state register? The input is big Y, capital Y, and the output is, okay, input and the output is small y, and it's a register. So how do you define a register in Verilog? How do you define register? So it's just always at post age of CLK begin if reset bar. Okay, so you can do something like this. If reset equals to 0, okay, then our small y will be S0. Okay, so we go to state 0. S0 is actually defined here, which is 0. Okay, so it means that if we reset, then our output of the state register will be basically 0. Okay, else, okay, so else we're going to say y is equals to the big Y. Okay, you can see here, so we are transferring there at the positive edge of the clock, and reset is 1. Okay, so reset 1, positive edge of the clock, then we are just going to transfer the big Y to the small y. Okay, so that is done. Now let's do the NS logic first. Okay, let's do this one. Okay, so let's do the NS logic. So here you can do always at, so what is the input and output to the NS logic? So the input is A and this, and what is this? This is Y. small y. Okay, as you can see, it's a feedback. So always at a comma y, begin. Okay, so what is the function there? What is the function that you want to have on the next state logic? So we have to look at the ASM chart or our truth table, right? So so if we look at our chart back again here, so you can say case present state S0. Okay, sorry, please. Okay, so if we state S0 and A equals to 1, what is our next state? Okay, we're doing next state logic, right? If S0 and state is A is 0, then what is our next state? So you can see here that I'm going to check the A. S0, if A is 1, then we can say that our big Y, which is the output of the next state logic, is simply equals to S1. Okay, else big Y is equals to S0. So you can see here that we are in state S0. If A is 0, we give Y is big Y is S0. Okay, if A is 1, we go to S1. Okay, so let's continue. Okay, so in state S1, A0, A1. Okay, so if A is 1, then you want to go to S3, else big Y is equals to S2. Okay, so S2, if A, so S2, 0, 1. So if A is 1, then we're going to go to S3, else S2. Okay, S3, 0, 1. If A, our big Y, is going to be equals to S0, else big Y is going to be equals to S3. Okay, so end case, and finally we do our last output logic. Okay, so remember that our output logic is Z equals to 1 when state 0. Okay, so Z is only equals to 1 when we are in state S0 or S3. Therefore we can say, okay, the data flow modeling style assign Z is going to be equals to 1 if the present state, which is small y, equals to S0, or present state equals to S3. Okay, so end module. Okay, so we can see here. Okay, so basically, again, if you want to recap this, basically what happened is we see that the output Z here now depends on the small y. So that's why we are checking here. Okay, if small y is S0 or S3, then we say Z is equals to 1, else will be equals to 0. Okay, so I think that's all for this part. We'll continue in the next part of the video.